In this video, we are going to look at how to estimate the population proportion P. So this, in other words, this is the binomial setup we were looking at in the past. So each trial with two possible choices, success or failure, with probability that probability of the success is P and the, otherwise Q. So we want to estimate P. Okay. So of course we pull a random sample. So in other words, in different words, we are looking at n independent identical trials. So when you pull a random sample out of that, okay, so you already have seen that the central limit theorem for that. For large n, the sample proportion, which is the p hat, is approximately normal with p, and the standard deviation is going to be the square root of pq over n. Okay, so the p hat is the sample proportion, which is the number of s values in your sample, and the sample size. So just like in the estimating the population mean mu, so we use this curve, which is that, and sort of like put in 1 minus alpha within that. So I'm not going to show you the derivation, but if you use the same trick, and you're going to end up with this confidence interval. So the idea is that here, from here to here, you're looking at 1 minus alpha, and then you need to do a couple of steps, and that will give you the confidence 100 times 1 minus alpha percent confidence interval for P. It's not for mu, okay? This is you need to follow the same procedure. The confidence interval for P is going to be the P hat minus the z table value square root of P hat Q hat over n, the P hat plus the same thing with the plus sign over there. Okay, so this is a approximate confidence interval, actually for two reasons. Because this is going to be correct for large n, that is one reason. And another reason is that in the formula I did not show you the derivation going from here to here. Actually you're going to end up with a P and Q here. We are going to estimate those two also. So we don't need the details, but this is approximate 100 times 1 minus alpha percent confidence interval for P. Alright, so here the condition n must be large so that np hat must be greater than or equal to 15, and nq hat must be greater than or equal to 15. In other words, this is the number of s in your sample. This is the number of f in your sample. Okay, see here, n times p hat is the number of s. The same way, this is the number of failures in your sample. Okay, so those two both values has to be more than or equal to 15. Okay, for you, so that way n is kind of big enough. Okay, so n must be large so that condition is correct. So there's another improved version of this thing, this interval, especially if you are dealing with not that big n. Okay, for small n little bit. Sometimes, you know, this may not be true. So if this is not true, especially for small n, this is a very good interval. Okay, this is a improved version. That one, 100 times 1 minus alpha percent approximate confidence interval for P. So is going to be like that. It's the same format. Okay, so P, instead of P hat here, you have the P tilde, and the z table value P tilde Q tilde. Okay, this is Q is 1 minus P, by the way. Okay, so it's the same thing. Okay, so this one part is 1 minus P, and this one the same thing with the plus sign. This P tilde, instead of that P hat, the P hat was over there, the number of s divided by n. instead of that, so P tilde is the number of S plus 2 divided by N plus 4. Alright, so especially if you are dealing with a small lane, this not the small lane, sorry, it's not the small lane, especially if you are dealing with without this condition. Okay, so this is a good one. So here anyway, so so you can, in the exams you can use this one. Okay, if you want you can do that, this is okay, you can use that. All right, but you need to check this condition. If you can use this one only if this condition is correct, otherwise you got to use that. Okay, all right, so let us look at a couple of examples. So in this example, in a sample of 100 tubes inspected, 20 were found to be defective. Set a 95% confidence interval on the true proportion of defectives in the entire population, entire production or entire population. Okay, entire production. So the P hat for the sample 20 defective and out of 100, which is 0.2. So the Q hat 1 minus P hat, which is going to be 0.8. So the 95% confidence interval for the proportion of defective items, this is P is the defective items, is going to be the P hat. I'm using the formula. That formula, Z table value square root of P hat Q hat over N, the same thing with the plus sign. And here you want the 95%. So with the Z table value 1.96. So 0.2, P hat is 0.2. So the the P hat value is 0.2, Q hat 0.8 divided by that. So the same thing with the plus sign over there. So calculate that. Make sure you keep at least 4 decimal places accuracy. Okay. So this value is that. 0.2 minus that, 0.2 plus that, so that value is that. So that's the confidence interval. So now you need to check whether this N is big enough. The condition is that the number of S in your sample, which is NP hat, which is 20, is more than 15, and Q hat is 80. If it is out of 100, if 20 are defective, the other 80 they are good. So these both are okay. All right. So if you want to basically use the other method I gave you, the better method, okay, the Wilson's adjustment. So this is good for the exam. Okay. So you could use this because this condition is okay. So this is all right. Okay. So the P tilde 20 plus 2 divided by 100 plus 4, which is that. So the Q is going to be 1 minus this P tilde value, which is that, 1 minus that. So use these two values in that formula right here, here, here. Okay, so that's about it. So that will give the interval. So now let us look at this example. So in this example, so here, so you want to estimate again the P, but in this your sample is 200. So 3 were victims of violent crimes. So you want to construct a 95% confidence interval, all right, for the entire population, proportion of Americans who were victims of violent crime. Okay, so if you look at NP hat, the number of successes in the sample, number of S in the sample, which is 3, so which is way less than 15. So technically you cannot use this, all right. So you have to, so in other words, you cannot use this because that condition is not there. So if you want to answer, you have to use this, all right. So now suppose you kind of did not even check that. You use this formula. So you are going to end up with this P hat, this with 95 1.96, the P hat, or this is N. So that Okay, so the p hat actually is going to be, so p hat value is going to be 3 divided by 200. Okay, so that value is going to be this thing. So then you are going to end up with this interval. See, like that. You can see that what happened. See, this is a confidence interval estimate for P. Okay, this is an interval estimate for P. You can see that this is a very bad estimate. We already know that P values supposed to be in between 0 and 1. So here you are getting negative answers. Okay, so this is not good. See, you see that? Because you did not have the condition to begin with. You remember that when we talk about the confidence interval, I said that I gave you a different condition actually. So like within +3 -3. So in other words, if you use that +3 -3, if you construct the confidence interval, put in 3 and 3 here, you're going to end up with a -1. So that's where that the original condition I gave you, different one, that condition I gave you. Okay, at that time even I mentioned that. Okay, so that 15 thing I mentioned that at that time anyway. So now, so you can technically you cannot use that. Okay, this is wrong. So you have to use this, the second one, Wilson's adjustment. So the p tilde, so here p tilde, which is going to be 20 plus 2 divided by 200 plus 4. All right, so if you calculate that, this p tilde value is going to be 0.025. So put those two values with that p tilde q tilde in there, you're going to get that interval. So see this one, you don't get that bad part, negative values. So this is a much better answer. So that's why I said that if you are dealing with a small n, this is a much better interval. Okay, so actually you should not use this for small n. Okay, all right, so that's about estimating the population proportion P.